As the reaction progresses, you want to monitor the reaction to make sure your starting material is being consumed and your product is being produced. The most common way for us to monitor a reaction is thin layer chromatography, or TLC. Now, most reactions can be monitored by TLC, but keep in mind, sometimes you'll run a TLC and nothing will show up. Some starting materials and products don't show up on TLC, and that just happens. Basic process is we take a TLC plate, and you can see that there's an origin line and just a mark where we're going to spot it. You have a spotter containing your material. You spot that on the plate by touching the spotter to the plate, and then that compound is on the plate. Then we place the plate in the TLC chamber that contains a solvent. And from there, there's a competition between the compound being attracted to the TLC plate and being attracted to the solvent. So if it's attracted to the plate, it will stick to the plate. If it's more attracted to the solvent will pull it up the plate. So here you can see that as the solvent runs up the plate, it's separating the two compounds in this mixture. The blue compound is more attracted to the silica gel plate. The red compound is more attracted to the solvent, so it gets pulled further up the plate. As you continue to develop, those two spots will further separate. And then where we pull this plate out, where the solvent stops, that's our solvent front. The TLC plate is made up of silica gel and silica gel is really polar. And polar compounds are going to attract to like molecules, so polar compounds are going to stick onto the plate more than nonpolar compounds. So what that means is if we compare these two, the blue compound is more polar because it sticks more to the polar TLC plate. The red compound is less polar. If you want your compounds to move further up the plate, what you want to do is make them more attracted to the solvent than the silica gel. So increase the polarity of your elution solvent to move the compounds further up the plate. Here's a table of common organic solvents, and you'll have access to this table through a link that you're provided. And what you can look at to help you predict the solvent polarity is the dielectric constant. So we see that right here. So what you can do is look at the value and predict relative polarity of things. So for example, cyclohexane has a pretty small dielectric constant of 2.02. It's quite nonpolar. But then if you jump up to something like acetonitrile with a dielectric constant of 36.64, it's a very polar solvent. So using this information will help you predict relative solvent polarity. Here's an example of a TLC plate you might get from a reaction. Your first lane is the starting material. The second lane is the product. Sometimes you'll see a middle lane where the starting material and product are co-spotted. That's not the case here. In this reaction, there's two starting materials, and we see where those spots show up. And then there's one product that's less polar than the starting materials. What you want to do is calculate RF values for these. And you can see that we have a ruler lined up here. The origin line is at 0, that's right here. And then we have our solvent front, which is right here at about 9.9. So then to calculate your RF for a particular spot, you take the distance a spot travels divided by the distance of the solvent front. And you should do that for every spot that shows up. So for example, the product is at about 5.5 centimeters. We divide that by 9.9 centimeters, and we get an RF of 0.56. There are no units associated with RF values because you're dividing centimeters by centimeters, so the units cancel. A larger RF value corresponds to a less polar compound.